In lecture 17 of Symmetries, Particles and Fields, we'll start off by giving you some more mnemonics really on how to use the Dinking diagrams to look at sub-algebras of Lie algebras, and in particular how to look for maximal sub-algebras as well. So we'll have to define those terms first. But then we will go on to look at representations of the Lie algebra in our Cartan-Lyell basis and start deriving some facts about them. Okay, so regular sub-algebras. So a regular sub-algebra of some Lie algebra is a sub-algebra just such that the roots are a subset of the roots of the Lie algebra. So let's take simple Lie algebra. L of G is a subalgebra such that the roots, we're going to call our regular subalgebra L of R for regular. So the roots of L of R are a subset of the roots of L of G. And also the Cartan subalgebra is also a subset. So it's called a maximum regular subalgebra if the rank is the same as the rank of L of G. So our Dinking diagram is a diagram of the roots. So if we just remove some of those, then we can find some of these regular subalgebras easily. So, for example, let's take, as I'm going to use physics notation, let's take the Lie algebra of complexified SU3. So I'm dropping subscript, suffix of the complex numbers here. So in this part, when I write to Lie algebra, perhaps I should, no, actually I should keep it really, because before I've used it without the complex suffix to denote the real forms. Okay, so this is the Lie algebra of the complexified form of SU3. And if we just remove one of the roots the remaining root is that. So, and this is the Lie algebra of complexified form of SU2. So in other words, I can take another one of our Lie algebras. So again, if I remove one of these, this also contains SU2. And this thing on the left, if you look at our table last time, you'll see that this is the Lie algebra of SO5. Now let's take something a bit longer. Let's take something with 3 roots, Lie algebra of SU4. And let's cross out the middle root. So this removes the connections between the outer ones. So in other words, the Lie algebra of SU4 contains the Lie algebra. So this is, remember, this is the Lie algebra of SU2 cross SU2 without a connection. That's how we denote a semi-simple Lie algebra. And it's one of the exercises to show that that Lie algebra is the same as the Lie algebra, or at least isomorphic to the Lie algebra of SO4. This next one is useful for grand unified theories. So some grand unified theories use, for the part of the symmetry connected to the identity, they have the Lie algebra of SO10. And if we say remove that, then we have, well, SU5. So Lie algebra of SO10 contains the Lie algebra of SU5. Okay, now we're never going to find maximal subalgebras by removing roots, because maximal subalgebras have the same number of roots. So to find maximum subalgebras, what we consider is a system which has the simple roots that we've already drawn in the Dinkin diagram, plus the lowest root. In other words, minus the highest weight of the adjoint representation. So the most negative root. So this one is denoted by the same diagram. What usually one uses math notations for these. You use the math notations for the simple roots system, i.e. without the lowest root, and add a prime. So sometimes called an affine Lie algebra. Now, it turns out that there's a unique one for each simple Lie algebra that we had in our other table. There are affine Lie algebras are important in string theory and in conformal field theories. They're actually infinite dimensional. But anyway. So for each simple Lie algebra that we had in our table, so I'm going to denote them in the maths notation now with a prime. So remember, we usually have n roots, but we add an extra root on, and the extra root comes above and is connected to the ends. Bn prime, so remember Bn prime is we have n roots here, and we add, turns out that we add the additional root to the second one. Cn prime, okay, so before we had n roots this way, and we add this one on the left hand side. So these now all have n+1 roots, these affine Lie algebras. Dn prime was like that, and we add an additional root here. We have the affine exceptional algebras. So before we had this, and it turns out that the additional root goes there for E7 prime. It turns out the additional root goes on the left-hand side for E8 prime. It also goes on the left-hand side. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. And so we have that one. And F4 prime, again, it goes on the left. G2 prime, again, it goes on the left. All right. Now, notice with these pictures that there are now, with the affine Lie algebras, there are now n+1 roots. So, okay, the reason we've introduced these, what's going to be interesting for us is that removing any root, it turns out, gives a regular maximal subalgebra. So again, we're not going to prove this. We've got bigger fish to fry. So to give you some examples now, let's have a play with these. So let's look at A4 prime. Well, A4 prime. Oh, sorry, I think I've got this n+1 wrong. Yeah, this should be A3 prime, sorry. The n+1 is correct. that's right. So A3 prime looks like this, so it doesn't matter which roots we remove. We get this one. So this is actually, so this is the original algebra A3 that we started with. So what all this says is that A3 contains A3, and so this is no use to us. Let's take a more helpful example, B4 prime. So B4 prime looks like this. Okay, so we can remove various roots. So if we remove this right-hand one, we get this, or if we remove the middle one, of course, then we have this. Or if we remove this one here, then I'm sorry, that's what happens if we remove this one. And if we remove the other one, which the one on the right hand side, we can get the following system. So yeah, if we move the second one in, remove the second one in. So these are the Lie algebras respectively. So on the left hand side, this is so B4 itself is the Lie algebra of SO9 in physics notation. And this contains, so here we have the Lie algebra of SO8. Here we have the algebra of SO5 cross SO4. It's one way of writing it. And here on the right hand side, we have the Lie algebra of, for example, well, we've got SU4 cross SU2. And I could also write these as, so these are examples really. I mean, you can, it's also the Lie algebra of the same thing when you mod out some discrete group. But I mean, I could write these, I could write this last one, for instance, instead. Of course, so this is more generally what the Lie algebra looks like, but I'm kind of not doing that in each case just because it saves writing. Okay, let's give you one more case. D5 prime. So this one looks like the following. Okay, so well, there's various ways that we could remove this, but one interesting one. Again, this is for grand unified theories. So the original D5 is LSO10, and it turns out that the maximal regular subalgebra, or a maximal regular subalgebra of this, is what's called Patti Salam. So this is important in terms of grand unified theories. All right, fine. So just to remind you, the Dynkin diagram really is an encoding of the Cartan matrix. The number of nodes tells you the size of the Cartan matrix, and in fact you can reconstruct, as we said before, the whole of the Lie algebra from the Dynkin diagram. So first, we determine the Cartan matrix A. And this is just read off the diagram. So A then determines the roots in this dual space to the Cartan subalgebra up to one undetermined vector. So in other words, you can scale, as long as you don't make it zero, you can scale the length of that vector, and the other ones will all scale appropriately, or you could rotate it. So everything is with respect to one particular vector that you sit down, which has got no particular physical meaning to it. So it's really the relative angles and the relative lengths of the roots that's important. So then we can reconstruct all the roots by forming root strings. And these have a length Lij, which is 1 minus Aj, and that this is some natural number. So let's give you an example of this reconstruction. Simple example. Let's take the Lie algebra of SU3. So of course, our Dinkin diagram is just two nodes with a line between them. So we've got because we have two nodes, we have a 2 by 2 Cartan matrix. There are twos always down the diagonal, and this one line means there's a -1 on each off diagonal. So we call simple roots alpha and beta here. There's only two of them. And we have, this Cartan matrix implies that, so the off-diagonal elements tell us what 2 alpha comma beta over alpha comma alpha is. So one of them tells us this, which is -1. But it also, the other one tells us what 2 alpha comma beta over beta comma beta is. Okay, so because these things are equal, we deduce that the length of beta is the length of alpha. And we also deduce from that cos phi, the angle between them, is -1/2. So phi is 2 pi by 3. So we can draw our simple roots. So as I said before, alpha is some length, but whatever that length is, beta has to be the same length. And I've just put alpha along the x-axis, but I could rotate it and beta would rotate accordingly. But what's important is that the angle between them is 2 pi by 3. Okay, so the length of the alpha string through beta L alpha comma beta is, remember, is 1 minus 2 alpha comma beta over alpha comma alpha. And so this quantity, this fraction is -1. And so we get in total 2 for this. So what this means is alpha plus beta is a root. And then the string terminates. Because the length is 2, so we start off with beta, and that's one of them, and alpha plus beta is the other one, and there's no more room for any of the others. So far we have, in the positive roots, we have alpha, beta, and alpha plus beta. Of course, we have the negative roots, which are just minus the positive roots. So let's plot. This will be helpful to us. Let's plot alpha and beta. Let's plot all of these roots. So alpha plus beta, you'll notice, is here. So this is pi by 3, that's pi by 3. And then we have some reason. All of these angles are pi by 3. And that's our root diagram. So this is our root set phi. Okay, good. Now let's begin to talk about representations of the Lie algebra. Suppose big lambda is a representation of the Lie algebra. So our representation of it, little d, is a map. Well, it takes elements of the Cartan-Weil subalgebra, the Cartan-Weil basis, to some matrix which is n by n of the complex numbers over the complex numbers. So okay, our elements of the Cartan subalgebra become some n by n matrices made of complex numbers, and E alpha goes to some matrices representing E alpha. And of course, as we said when we introduced representations, and several times since, these representation matrices satisfy the Lie bracket conditions. So let's assume for now that our Cartan subalgebra representation is diagonalizable for all I. So by the fact that little d is a representation, we know that d of hi commutes with d of hj, because of the fact it's a representation, this has to be d of hi commuting with hj. Which is 0. Now, this implies if you've got two matrices, these two Ds, so this is for all I and j. Okay, these are between 1 and the rank. So these two matrices commute by this equation, which implies that the DHI, the set of DHIs, are simultaneously diagonalizable. So this is a result from linear algebra and vector spaces. You can see the book for the proof. It's based on, well, finding the eigenspaces of A and then building up a diagonalizing matrix beta based on those eigenspaces, and then proving that each eigenspace of A is also an eigenspace of B. Okay, so if we take some space complex numbers to the n, this is spanned by the eigenvectors of DHI. So we can write V is the direct sum of lambda in S of R. Oh, sorry, S of D. V lambda, where if V is in this eigenspace, so this is the sum of the eigenspaces basically of D of HI. And so lambda I is just some complex number where I is from 1 to R. Okay, so lambda, so this R dimensional or this rth length vector is called a weight of the representation. Sorry, this should be. And the set of weights is SD here. So in general, these weights have a multiplicity. Just given by the dimensionality of the eigenspace. So it's bigger than or equal to 1, it's some natural number. I should just say that as a natural number. So note that The roots are the non-zero weights of the adjoint representation. And there's, in other words, there's one for each E alpha. And the adjoint representation also has R0 weights. Since there's one for each HI. You can get all of those things from just looking at the Lie algebra, because the adjoint representation is the natural rep on the Lie algebra. Okay, so now let's consider the action of some step operators on our vectors V. D of E alpha on V, which is in this eigenspace. So so our representation of HI acting on our representation of EI acting on V. Well, we can just use the commutation relations here. So, you know, we add something on and then take it away again in the commutator. So all of this acts on, damn, how do I move it? Oh, I'm going to have to write this out again. Sorry. So all of this acts to the right. So D, HI D E alpha, V is equal to D E alpha D HI plus the commutator. Okay, so we know what this commutator is, because, well, D of HI acting on V gives us lambda I back times V. This thing gives us alpha I times V times alpha I times D E alpha. So this is lambda I plus alpha I D E alpha V. Now, note that this thing now is different. This is the ith component of the root alpha, not the ith root, which we use this, we discriminate between the two things with the vector in kind of using the ith root is a alpha I vector. Okay, but without the vector underneath, it's just the ith component of this one particular root. Okay, so we recall that for each alpha, we have a set of SL2 generators. So for each simple root, so HI is, remember, is H alpha I, and EI plus or minus was E plus or minus alpha I. And our Lie algebra, the final form of it was that, of course, hi, hj is 0. Hi and ej plus or minus was plus or minus aji, e plus or minus ej plus or minus, and ei plus and ei minus is hi. So there's no sum on these. So okay. So and then ei plus or minus and ej plus or minus generates new basis elements. And then all of the brackets are 0. So we have that, for example, ei plus and ej plus is adjoint of ei plus, which is proportional to e alpha I plus alpha j if alpha I plus alpha j is in the root set and 0 otherwise. So the alpha I string through alpha j has length 1 minus the element of the Cartan matrix A, J, the jth element. So this, well, let's call that. So this implies that if we put the adjoint representation of I plus or minus, we try and raise it by that length, we're going to get 0 because the string must terminate at that point. So it can be shown that this, along with the Lie brackets above, uniquely determine the Lie algebra. Okay, so now V is a representation space to some representation which we'll call d alpha of SL2 alpha. In general, d alpha can be reducible. So for all V in the eigenspace V lambda, we have that the representation H alpha acting on V. So if we can use our equation 6.4b, and you will, if you look back and substitute in, you get something proportional to the representation of hi times a factor, and this factor was kappa to the -1 ij alpha j. And we get, there's an additional factor of 2 over the length of alpha squared. Okay. And so that's acting on V. So I've just substituted in for this representation of H alpha. So this is equal to 2 over alpha comma alpha capital -1 ij alpha j. So d H alpha acting on V just gives us back lambda I times V. And okay, so this gives this this middle factor is twice. So we get the inner product of alpha with lambda here. So because this is a representation of Lie algebra of SU2, the complexified Lie algebra of SU2, we know that this has to be an integer. And this will allow us to develop further this analysis of representations of general of Lie algebras of general simple groups with the additional conditions of being compact and complex, etc. Okay, so we'll develop that more next time.